Okay, so let's start. Okay, so welcome everybody to the seminar today. So so today we are very happy to have Lincoln Hong from University of Oklahoma. And Lincoln Hong used to be a student here and also the RA here in NCTS. So it's a homecoming. Yeah. So welcome back home. And also, and he's going to talk about the Nash problem over 3-4 terminal singularities. So please.
Okay, thank you for introductions. So it's my pleasure to be back to here to introduce my current work. Before when I was a RA, the center is in the astronomy building. So for me, this is a new home of the coming back. Yeah. So today I will talk about my current work on Nash problem. So before we start, have you heard about something like arc space or Nash problem before? No. Okay, that's good. Okay, very good. Because in today's talk, I have prepared a bunch of preliminaries for describing the Nash problem over singularities, including like arc spaces and the Nash problem. So for the first four chapters, they are like a preliminaries introduction to the whole Nash problem. And for part 5 and part 6, they are my current work so far. So first, motivation. So the motivation for Nash problem is we try to characterize some birational information of a given singularity on a variety over C. We mainly focusing on two objects. The first one is the so-called essential divisors, essential variations. So they played the so-called birational invariant of the single points on a variety, which can characterize the singular locus independent of a resolution. Then I will introduce this data, and the thing to study essential divisor, essential variations are called Nash components and Nash variations. And I will also introduce this data. And in this talk, our variety are always integral separated scheme of finite type over K, with K is a very good field. K is 0, algebraically close, like complex numbers. So intuitively, you can think about these kind of examples, like a fine variety divided on fine space. So let's briefly review singularities. Singularities. Singularities essentially means that the eyes of human being cannot see. So this space are called singularities, right? And in other words, regular points, they are the points that you can put the parametrization near this point, which means you can parameterize the space of containing singular points. The points that we cannot parameterize are called singular point. And we know we have learned from analysis, we can use implicit function theorem to characterize a point is singular or non-singular. So in particular, S is called non-singular or a smooth variety if it is a non-singular at every point, which means it is a manifold. It can be parameterized everywhere. So some typical examples are like this is so the first one is our favorite example. A2 we consider y squared minus x cubed equals 0, and obviously it has a single point at the original point 0, 0. You just need to calculate the Jacobian of this equation. Then, and it is easy to check that it is singular. Okay, yeah, then we have more examples of single points and smooth point. Okay, and in birational geometry, there's a very classical tool to study singularity, which is the so-called resolution singularities. Okay, so then we have that X be a it's here. Okay, so that X be a abstract algebraic variety with some singular locus, sig X. So a resolution of singularity of X is a proper birational morphism from a smooth manifold Y. Smooth variety Y to X, such that outside the singular locus, they are isomorphism. Okay, and roughly speaking, a resolution singularity means that we can obtain a smooth model Y such as to make the original X whose points are singular to be smooth. Yeah, we just try to make some like birational operations to make it smooth. Okay, and we also know its existence, right? Because we have the famous Hironaka's resolution singularity theory. So that X be a field of characteristic 0, and we can always construct resolution singularities with some of the conditions on the exceptional locus. Okay, and also it is arithmetic, which means that we can always find out the resolution by successfully blow up the smooth variety contained in a single locus. Yeah. Okay. By general, resolution of singularities, they are not unique. Yeah, because Hironaka's way is not the unique way to resolve singularities. You can go to other textbooks to find other types of singularities. Okay, so but you see, by applying resolution of singularity, so if you have a single variety, you successfully apply resolution of singularity by successfully putting blow up, then the singularities will produce a bunch of exceptional devices on your smooth model, right? Okay, yeah. And furthermore, we can blow up further to obtain this essential model to essential set to be essential devices. Okay? Yeah. And so in some sense, these essential devices can be part of the information characterizing such singularity, right? However, we know that resolutions, they are not unique. So if we have two different resolutions, this resolution may produce a bunch of essential devices. That resolution can produce other bunch of devices. So it seems that devices on the smooth model, they have a bunch of ways to describe the singularities, right? But however, we are doing birational geometry, right? So, and notice that although we have a bunch of resolutions, we know that any two resolutions, they are birational to each other, right? Because they are birational power morphisms, right? So it is natural to investigate if any essential device on all resolutions which can be birationally connected to each other. Or we can consider the so-called, if I have a smooth model on it, we can kind of to see that, does this device can be transported, birationally transported to another smooth model. And if you are given any other, maybe the third resolution, maybe we can see that it can be transported to a third resolution. Yeah. Okay. So in this sense, we can consider all these kind of devices, which can help us characterize the singularity. So this is the so-called essential devices. Okay. So apparently essential devices, what are they? They are devices appear on all the resolutions of our single varieties. Okay, okay, so far so good. Okay, okay, so
essential.
that's right. That's right. Yeah. Yeah. You disclose my examples in the following slides. Yeah. 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 I'll talk about this. All right. So, okay. So let me briefly formalize this concept. So what does it mean? What does it mean that devices appear in other resolutions? Okay. So let's consider two power biracial morphisms from X1, X2 to our single variety X, while F1 and F2, and assume that X1, so right now we have this scenario, X1, X2, while F1 and F2. Okay, so assume a divisor E surviving on X1. Okay. Okay. All right. So we can, okay. So except for the single locus, we know that F2, we know that F2 inverse, F2 inverse composite F1 will give you an isomorphism, a generic isomorphism between X1 and X2, except for the exceptional locus, right? So how do we transport our exceptional divisor from X1 to X2? Yeah. So here is how we formalize, because we know that X1 and X2, they are normal. They are resolution, right? So they are normal. So normal means that if you consider if you consider the largest open set making X1, X2 birational isomorphism, its codimension in X1 will be at least 2, right? Which means that the intersection of E and U will be non-empty. So therefore, if as long as it's empty, we can use this guy. You can use this guy to transport the intersection of E and U to X2. Okay, and then take closures. Okay, so this is what I say appears. So the thing we transport into X2, we call it the center of E on X2. Okay, yeah. We say that E appears on X2 if the center of E on X2 is also a divisor. Okay, yeah, so because when you transport to here, the exceptional set on X2 might be not a divisor, they might just some higher codimension universal set. So we say that it appears on X2, it means that it appears on X2 as a divisor. Okay, so so for every resolution, we can consider a bunch of divisors, and we can define the equivalent relation between these two divisors if E1 is equivalent to E2, if they appear as centers to each other. Okay, so that means that E1 is equivalent to E2. That means that E1, if you transpose into X2, the center is E2. Then we will say they are equivalent. Okay, and this equivalent class is called an exceptional divisor over X. Okay, yeah, that means that so roughly speaking, it means that okay, we have a divisor, it is surviving on some biracial model over X. Okay, so also okay. Okay. Okay, and notice that we know that divisors can induce because we know that the localization of the structure shift of X localized on E can induce a divisorial variation, right? So which is the variation order or rational function along E. Okay, so So by connecting the above equivalence relation, we can know that we can see that if two devices they are equivalent, even only if they have the same variations inducing. Okay, yeah, this way to this way, they are easy. From this way to this way, you can use the same argument as I described for defining center to say that, okay, if two variations are the same, then we can try to construct a higher model such that E1 and E2 appear on X1, X2 to each other. Okay, so in this sense, you see, potentially you see that if E1 and E2 they are connected to each other, variations can be potentially to be invariant, describing our singularities, right? Because singularity produce devices. We have a class of devices, and this class of devices can produce variation. So we have a connection between singularities and variations. Okay, yeah. Okay, so these two, the definition of essential devices. Okay, so an essential device E over S is called essential device over X. If what? If you consider all resolutions. For all resolutions, such E, the center of E transporting to all resolutions. They are the center of a resolving locus. Okay. Okay. Yeah. So yeah. Okay. So if we have, yeah. If here if F1 and F2 they are resolutions, we say E is essential. It means that if we transpose E to X2, if E appears on the exceptional set of X2, then we say E is essential for all resolutions. Okay, so this is just a mild comment. Okay, so examples.
So in your definition, that depends on Y, depends on resolution, or you need to choose the some higher model such that all devices appears.
Oh, you mean for definition of essential?
For the set.
The set. Oh, this set. Right. This set you need to choose you need to choose F. Yeah. Yeah. It depends on F only. Okay. So any questions? No. Okay. So examples. So let's take a look of some examples of essential devices. Okay. So the very first example is singular curve. Okay. We know that for singular curves, it has a unique canonical resolution singularity, right? It is nothing but the normalization of our singular curve. Okay, so yeah, so obviously, all devices on the normalization are all essential devices of X. Okay. Right, so the essential devices over S are all the devices appear on the normalization. Okay, secondly, if you consider the singular algebraic normal surface, okay, so that X has be a normal surface with a singularity small x. Okay, okay, and we know that for algebraic surface, if we consider an arbitrary resolution, it can be uniquely factored through a so-called minimal resolution, right? Okay, so you can see that as long as every resolution can be factored through such morphism, the devices appearing on the minimal resolution will be essential for X. Okay, so we consider such decomposition or universal component for the minimal resolution. yeah, we know that X is normal, so each Xi, they are curves. In this case, they are divisors. Yeah, so we know that the essential divisors are these curves, E1 to ER. Okay, so the first example is like Professor Ding, he mentioned non-raw divisors. Yeah, so okay, so a variety E is called birational rule or rule. It means that as a variety, it is birational to some variety F class P1. Okay, and there's a proposition telling you that if E is an essential divisor of such morphism Y to Y prime with a base manifold is smooth, then E is rule. Okay, directly apply this proposition, we can see that if we have a divide, if we have an exceptional divisor which is non-rule, then this divisor will be essential. Okay, so and the reason is not hard. So you can if such divisor is non-essential, then we can just all right, so the reason is because fix this divisor which is non-rule. If there's a resolution such maybe let me write here. You write again X, Y. We have E. This is non-rule. Okay, assuming it is non-essential, that means that what? That means that we have a resolution of X from Z to X such that E does not the center of E on Z is empty. It does not appear on Z. Okay, then we can take a common resolution of Y and Z to get a higher model. So this E will be also transported to this higher model, and this E will remain non-rule, which contradicts to this proposition. So it proves that any non-rule essential divisor is essential. Okay, so this is a brief introduction to essential divisors. Okay, any question? Nope. Okay. Okay, so arcspace. Let's go to the second section. Okay. Okay, so firstly, let's take a look what is an arc of a variety. So I have now modified. Yeah. This is my old version of slides. Okay, that's fine. Okay, yeah. So intuitively, let's talk about what is an arc of a variety. So that XP and a phi variety are defined by M equations, F1 equals 0 to Mn equals 0. So what is an arc of X? It is a solution. It is a formal power series solution of such equations. Okay. Yeah. So geometrically, you can think that what is an arc? An arc is a formal analytic curve lying on our variety. Okay. Yeah. So yeah, algebraically, if an arc is an n-tuple of formal power series, such that you plug in such x1 to xm, you get all equations equal to 0. Okay, and if we collect this arc together, we collect all such arcs of X, we obtain a big set of arcs. We call it the arc space of X. Yeah. Okay. I have written here, but yeah, but I failed to pop up my new slide. So yeah, just listen to me. Yeah. Okay. This is for a fine case. If you know some scheme theoretical algebraic geometry, so there's an alternative definition for arcs. So let X be a skin over K. An arc is actually a morphism from spec of form power series over K to X. This is called an arc. So if you have some like algebraic geometry background, you know that this is using the language of functional point, right? So that means that for a scheme, any points, no matter it is cross point or generating point, it can be realized as morphism from some for some ring to the X. Yeah, this is the point of view from Grothendieck. Yeah, so it is an arc of a form power series value point of X. Okay, so if X is a finite variety, again, the arc, if you carefully operate this definition to the case X is a finite variety, you can verify that, okay, from this definition, this arc is actually a form power series solution of X. Okay, yeah, for example, if you take this finite variety, y squared minus x cubed equals 0. Yeah, as a scheme, it is C of this is C of xy quotient by y squared minus x cubed. Okay, then you operate the definition of functional points. Then you can easily to see that, okay, it is equivalent to say that we have a pair of form power series satisfy the original equation y squared minus x cubed. All right, so let's take a look at its computation. That f of xy to be y squared minus x cubed, then alpha beta to be a tuple of form power series. Okay, so alpha t is a form power series. A0 plus A1t plus A2t squared over 2 plus da da da. Beta is B0 plus B1t plus B2 t squared over 2 plus da da da. Then we can plug in to the original equation, right? So so we have alpha of t, beta of t. So we have beta of t squared minus alpha t cubed equals 0. Okay, then if you plug it in, you have B0 plus B1t plus B2t over 2 square plus da da da, the whole square minus A0 plus A1t plus A2t over 2t square plus da 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 cube equals 0. Okay, and we know that form power series they are uniquely defined by coefficients, right? So we can try to compare the coefficients even of this t. Okay, like for example, you can expand this equation and you look at the zero order term, first order term, second order term. Okay, then it is now hard to see that for zero order term, it is the original equation y squared minus x cubed. The second order term is actually the equation of the tangent line, which is the gradient f of a0 b0 dot a1 b1. And for the second order, it is the quadratic approximation of this y squared minus x cubed. Okay, so from this computation, you can also write what is an arc. An arc is actually a pair of infinitely many numbers, a0, a1, a2, da da da, b0, b1, b2, da da da, satisfy the equation, the original equation equals 0, the gradient is 0, the second quadratic, the quadratic approximation is 0, cubic approximation is 0, da da da. Yeah, so actually you see that. Okay, then you collect it then together to form the R space of X. Okay, so you can see that in this case, the R space of X, it is not a variety, right? Because the set is given by infinitely many equations and it has infinitely many coordinates. So this is a scheme of infinite type over K. Okay, yeah. All right, and if you know the language of fundamental points, arc space is collecting all the morphisms from space K of T to X, right? So this is the capital home from space K, Kx to X. Okay, from the previous calculations, from previous calculation, we potentially can modify this. So notice that this is a representable functor. So we can write this guy in the form of home of spec K, common this guy. Okay. So actually, if you run the argument, this guy, oh, I have not. This guy x infinity is actually the space I mentioned you before. So this is this one. Yeah. So this guy is actually Planar representative of such functor spec K of T to X. Okay, yeah.
What is the skin structure you put on X infinity?
Or the skin structure.
Yes.
Yeah, yes. So okay, the skin structure. Oh, okay. So
There is a projected limit of
oh, okay, yeah. So actually from this case, you can consider the truncated spec. You can consider like K of X over X to the N. Okay, then the skin structure will come from the projected limit of this guy, of a truncated morphism. Okay. Yeah. So okay, and if X is covered by a lot of affine charts, the skin structure, the structure sheet will be provided by the spec of C of yeah. In the previous example, the structure sorry. Yeah, the structure sheet will be provided by K, common is A0, A1, A2, B0, B1, B2, quotient by F, gradient F, Hessian F, cubic quadratic F, and so on. Okay. Yeah. So the skin structure is also provided can be treated as provided by such affine charts. Okay. Okay. Any other questions? Okay. So yeah. Okay. And actually, arc space it has been exist in the concept of physics for a long time. Yeah. If you notice carefully, you can think that okay, X is a space that a particle will move along by some patterns. And what is the R space? R space is a parameter space of such article, encoding what? Encoding its position, velocity, acceleration, jerk, acceleration of jerk, and so on. Yeah. So for example, if you think that this is your space, so the trajectory of particle is your alpha t beta t. This AIBJ, they encodes. This is the position of our article. This is the velocity of a particle. This is acceleration. Yeah. So this is actually the so-called phase space of the given X. So we have. Okay. So yeah. So this is what I mentioned here. The arc space is an infinite dimensional phase space of trajectories for this particle. Okay. Yeah. So we can treat that X infinity as a bundle. of X. Yeah, because it plays a role of phase space. Okay, so we can consider the canonical projection from X infinity to X, mapping the all physical information to the position A0. Okay. Okay, so questions? No. All right. Okay. So next conjecture, next problems. Okay. So we finished looking at essential variations and arc spaces. So right now we can try to formulate the description of the next problem, next conjecture. Okay. As I mentioned before, given a singularity, we see that essential devices, they play a potential role of being birational information for such a singularity, which means that, okay, so if I resolve singularities, I can see that, okay, if an essential divisor, it appears in every resolution. Okay, but technically it is unrealistic to see that a divisor, it is essential or not, right? Because if you want to see it is essential, you need to transport your divisor to all resolution to see that, okay, does it appears as a divisor on other resolutions? Okay, so this is kind of like we want to use some intrinsic way to characterize essential variations. We want to characterize essential variations of an X without using resolutions. Okay. So what is this? This is coming from arcs. Okay. Then this is proposed by John Nash. So his idea is the following. So he tried to lift arcs, which is passing through the singularity of X, and then try to lift these arcs via the resolution to see that what is the behavior of such arcs. Okay. Okay, so let's try to formalize this idea. Let X be a variety of a K with single locus, sin X. Okay, consider arcs passing through a single locus, sin X. Okay, so right now we just introduced the canonical projection from the arc space to X, right? So consider arcs passing through single locus, sin S, is equivalent to consider the preimage of the sin S while in the preimage of X. Okay, so the idea is the following. Okay, so let's see. Okay, so assume this is our X. So we have a single locus here. Okay, then we consider all arcs are passing through the single locus. So geometrically, we can treat this picture like, okay, we have a lot of small LED curve passing through this point. Okay, then then scheme theoretically, for every arc, we know that if you use the fundamental points point of view, we can treat it as a morphism from the residual field, from a spec of residual field of X with a double bracket T to X, such that the close point of K double X will map to the single locus. Right. So okay. Then we can topologically decompose our X inverse sin X. Okay, so this pi X inverse sin S, we actually call it the Nash set of X. Okay, yeah, we call it Nash set. pi x inverse sin x. The Nash set of x. Okay. Okay, so topologically, we can decompose into the union of Ci and Di. Okay. So, okay, where Ci are irreducible components with a point x is in sig S corresponding to an arc, such that if you consider its corresponding generating point, it is not belonging to the single x, and DJs are irreducible components. Okay, and these DJs are called Nash components of x. Sorry, I have not modified it. Okay, yeah. So what does it mean? So it means that so if you consider the red part of this picture, it can be decomposed into this kind of C1 union C2 union union to Cm, maybe union D1 union D2 union to DL. Okay, so this C1 to Cn, they are Nash components, which means that for each Ci, it is called Ci. Okay, then we have a bunch of arcs. Okay, so graphically you see that if this is if these points correspond to the point that the arc passing through, the other part of arcs does not contain in a single locus, right? So geometrically we think that okay, we have alpha t, we passing through this is a single locus of x. But besides, okay, so maybe it is bigger, maybe the single locus is here. Yeah, okay, but besides this, other parts of alpha t, it does not contain the single locus of x, right? So this is our intuition that an arc based on single locus of x. Okay, so we collect. Okay, so we collect all such arcs. This will form the union. This will form the C1 to Cn. Okay. Okay. Yeah. So maybe that. Okay. Then what is DJ? DJ is something like if this is DJ. So if your single locus looks like this, it is a curved curved singularity. DJs will contains arcs, maybe passing through the single curve transversally, or it will be fully contained in our single curve. Okay, right. So okay, so roughly speaking, you can consider Ci. They are arcs passing through the single locus transversally. DJ, you can think that other kind of arcs, which could be transversally passing through, or it can become fully contained in a single locus. Okay, so for such Nash set, we have these two kinds of possibilities. Okay, and however, you see that this DJ is pretty complicated, right? However, in our case, we don't need to care about this. Why? Because our K is characteristic 0, and so maybe let me briefly skip this. This is the theorem for Cauchy's. Okay, so you don't need to care about the details of this lemma. So this lemma is essentially tell you that if your ground field is of characteristic 0, there will be no DJs in our Nash set. There are only CI appear on our Nash set. Okay, so okay, and this CI in this scenario we'll call it the Nash component of X. Okay, so right now in this case we don't need to care about DJs. We just need to care about C1 to Cn. Okay, right now let's go through the Nash idea. Okay, so here's the following. Let F be a resolution singularity of X. Let Ci be a Nash component of X. Then we consider the open set of Ci such that the generating point of arc does not contain in a single locus. Then this arc can be uniquely linked to the resolution. So the picture is something like this. Right now we have X is a single variety. We apply a resolution F. So it goes to Y. Okay, so on Y we have a bunch of extensional set, right? Maybe this is this one. Maybe this code E1, E2, E3, E4, something like this. Okay, so this lemma is actually telling you that this arc will be uniquely linked to maybe this one, and other arcs will be linked to this one. Okay, so it is actually telling you that okay, different arcs is algebraically possible. Okay, and the proof is pretty easy. You just need to know the variety criterion or properties, then you can easily to prove this lemma. Okay, so let alpha tilde be the definition of alpha X. Okay, so apparently we have an arc. Then by F we can lift to a new arc on Y such that it is based on extensional state. Okay, and if you simply look at the picture, you will see that this arc, we just said that it can be lifted to some extensional set or extensional components arbitrary, right? It seems that there's no pattern how the arcs can be lifted onto, right? So this is how the Nash proved in this 1995 paper. Okay, so he proved that this arc it is not only lifted into a divisor. The component content of arc will be also lifted into the whole divisor such that the arc based on. Okay, so let F from Y to X be a resolution of X. Let Ci be a Nash component of R to sig X. Then Ci be the generating point of Ci. Okay, so the first one is what I say. The lifting of the components will be fully occupy the extensional divisor such that the arc you pick lift onto. Okay, and secondly, as long as you lift a Nash component, you will fully lift to a divisor, right? So he also proved that the divisor, which is lifted by some Nash component, it is actually an essential component of Y. Okay, so right now we potentially have a map C1 to Cm goes to E1, E2 to ER. Okay, so let's call this map capital N. Okay, so from this theorem we have like C1 will be fully mapped to E2, C2 will be fully mapped to maybe X6, something like that. Okay, so we have the induced map from the Nash component of X goes to the essential devices over X. And the third thing is the Nash proof that this map is injective, which means that different Nash component will be mapped into different will be mapped into different essential devices. Okay, so you've seen that, yeah, and this map is called a Nash map of X. Okay, so because this map is injective, so you can see that the number of irreducible components of the essential set is finite. So there are only finite many Nash components of X. Okay, so and this gives us a potential intrinsic way to help us detect an essential device over X is essential or not. Yeah, so you see that this correspondence is pretty intrinsic, right? Because if we want to see because Nash components, for obtaining Nash components, we don't need to take in resolution, right? We just need to consider all arcs passing through single locus of X, then we consider all components and their generating points, then using Nash map, we can know that each component will be mapped into some essential variations over X. Okay. Okay, and furthermore, if you use the language of variations, the essential device will induce us. It will induce variations VALEMI, which is called essential variations.
I have a question about
Yes.
Previous slides.
A previous slide. Okay.
Why do you consider image of generate point? Because can you just consider image of the component? Still previous in the statement of Nash theorem.
Oh, you mean
Yeah.
this one?
Can you just consider direct the image of the image of C?
Oh, in this case, yes, we can just consider directly consider the image of C. This is okay. Yeah. Okay. So the reason we consider the generating point first is it is convenient. Secondly, this is not in our case. Secondly, if your field is not characteristic 0, you will have this DJ part.
Yes.
Then this DJ part then you might have trouble if you map your DJ into your device. It might not be fully occupied.
Okay. Well, by your previous lemma, you can first lift CI to arc space in Y.
Yes.
You can look at projection.
For the
This is the same one.
Yes, for a single arc, I can lift. But for the components, it is non-trivial, right? So this is a theorem. Okay, that's okay. Maybe we can talk about this later. Okay. Okay, so just let me. Okay, so this slide is telling you that if we have a device which is essential, I can consider its associated variation, which is called essential variations. And for a Nash component, I can consider its associated variations, which is defined by this. It's called a Nash variations. And by some complicated algebra argument, the injectivity of Nash map can be formulated as following the last statement. So for the second statement, we can consider the Nash variation over X. Essential divisor can induce essential variations. So the injectivity of Nash map can be formulated as the Nash variation over X will be contained in the essential variations of X. Okay, yeah, so we use the language of variations. Okay. Okay, and there's a very common example, there's a common example that you can try to solve Nash. You can try to describe the Nash map of this example. Yeah, because for this type of singularity, you just need to apply twice blow-ups to resolve the singularity. Then you can try to consider the Nash state of such X, then to try to see that, okay, which Nash state is corresponding to which devices. Yeah, but let me skip this. Okay. Okay, so given a resolution, we can lift an arc passing through the sinc X to get an exceptional device which is essential. Okay, and from the previous theorem, we know that Nash components can be uniquely mapped to the essential devices, which means this map is injective. Okay, so next it is natural to ask that, okay, given an essential device E, can it be realized as an image of a Nash map? So does there exist a Nash component such that you plug into a Nash map? It is an essential. It is itself. Yeah. So which means that is the Nash map surjective? Yeah. We know that Nash map is injective. So we can naturally ask that, is it surjective? Yeah. So the conjecture of surjectivity is called a Nash conjecture. Okay. Okay. So is Nash conjecture always true for any kind of singularity? So fortunately, the answer is no, in general. But we still have some special case that we can talk about. So for the original Nash paper, the Nash conjecture is true for all AN type surface singularity xy minus d3 n plus 1. And okay, and it is also true for a bunch of examples. So for example, like Bobadilla and Manipur they prove that, okay, if you have an arbitrary surface singularity of characteristic 0, Nash map are always surjective. Yeah. This is published in the Annal of Math. And we have other mathematicians, Jabert, Negrela, and Ishii. They provide a bunch of examples that Nash map is surjective. Okay, and for the first one, let me talk about this data. Okay, and furthermore, for some important varieties, the Nash map is surjective. The very important example is this one by Ishii and Kola. They prove that if you have any toric singularities, Nash maps are always surjective for any dimension. And furthermore, Hale proved that for the quasi-ordinary hypersurfaces, the Nash map is also surjective. Okay, counterexample. So it is false. The first example is also provided by Ishii and Kola. Okay, so they provide this example. This is a fourfold in A5. This guy has only one Nash component, but have two essential components. And also we have the Fernet, Johnson, and Kola. They provide counter examples for dimension 3. Okay, so we know that Nash map is in general not surjective. So the next question is, what is the image of Nash map? So the next step is we try to understand and characterize the image of a Nash map. This is a so-called Nash problem. Okay, so Nash problem is a problem that trying to characterize what is the image of Nash map. Okay, so a very big result for the Nash problem is the following. Okay, so the idea is we know that for surface singularity, minimal resolution is existing uniquely, right? But for higher dimension, the minimal resolution need not exist. But although minimal resolution did not exist, minimal model over X exists by BCHN. Okay, so in 2026, Dufresne and Docampo Alvarez, he's my advisor. They proved that so this is a result provided by Nash, right? Nash variations are essential. They prove that if we use the minimal model, they introduce the so-called terminal variations. These terminal variations is in the image of Nash map. So we have terminal variations, it's contained in Nash variations, and furthermore contained in essential variations. Okay, so yeah, this is the end of introduction. Yeah, any questions? Okay. All right, so the rest of the two sections are my current work or my PhD thesis. Okay, so from now on, I will talk about my current work on the Nash problem over free-fall terminal singularities. Okay, so right now here's the motivation. Okay, so I just mentioned before, for a single variety, Dufresne and Docampo Alvarez, they use the relatively minimal model over X to characterize the image of Nash map. Okay, yeah. So this is so that you recall that they introduced the so-called terminal variations by minimal models, and they prove that this is in the image of Nash variations. Oh, sorry, the image of a Nash map. Okay, so the idea is the following. So if you have a single variety X, then you try to run the relatively minimal model program. So first you try to apply a resolution on X. Then you try to do divisorial contractions. Okay, then maybe most of you know how MP works, right? So you can check that. Okay, so if a canonical divisor is not relative naive, then we can produce a divisor contraction to contract the -1 curve into a new model, right? So we have a bunch of divisors, then we end at the so-called M-mean, which is the minimal model over X. So, and it satisfies that the Kx mean, if this map is called F, this is F-nav, and X mean has only terminal singularities. Okay, yeah, this is the minimal model we encounter in this process. Okay, so the idea is if we produce such minimal model, this map is divisorial. So here we also have a bunch of divisors, E1 maybe to EL. This E1 to EL, they will induce Nash variations. Okay. However, this work fails. Okay, so this idea can be deal with all kinds of singularities, except if X itself has terminal singularities. In this case, if you run the relatively minimal model program, you will highly possibly obtain X mean is actually X itself. So if X has terminal singularity, there's no terminal variations over X. Okay, so for X has terminal singularities, we need new approaches. So this is kind of the motivation to study terminal singularities. Yeah, and right now I can only study free-fall because free-fall has been classified by Mondi. Okay, so let me give you a warning. For the rest of these two sections, all results are still not completely confirmed that it is correct, which means that there might be some mistakes we have not found it, but maybe from ODS you can see there are some mistakes appearing. Yeah, if you see some mysterious things, you can let me know. Okay. Okay. So my work focusing on two cases. The first case is Tori terminal singularities. The second case is free-fall terminal singularities with Gorenstein index greater than 1. Okay, so first let's talk about Tori terminal singularities. Okay, so this work is based on the work published by Ishii and Kola. So they fully solve the Nash conjecture for Tori singularities. So Nash mass over Tori singularities are surjective for all dimensions. Okay, so that X delta is a fan in NR. Okay, so this is their result. So that X delta be a single Tori variety induced by the fan delta. Then its Nash map is bijective. And furthermore, we can explicitly describe what is the Nash variation over X. It is uniquely divided by a minimal element of the interior of your single cone intersect the lattice. Okay, what does minimal mean? I will tell you later. Okay, then this is my result. Okay, so right now, so their result is for arbitrary single Tori variety, and my result is focusing only on Tori variety having only terminal singularities. Okay, so my result is for this kind of thing, for Tori terminal singularities, that E be a essential divisor over X. We know that its discrepancy, which is the coefficients, appear in a relatively chemical divisor with respect to E. We know that it is positive. I suppress that if it is multiplied by 1, then the inducing variation VE is a Nash variation. Okay, yeah. So this is okay, and the value of this result is this is true. Not only for threefold, it is true for n-fold. For n is greater or equal to 3. Okay, so let me briefly sketch the proof. So the proof is the proof is not hard. So it is essentially that because we know that for Tori variety, discrepancies can be fully written as in terms of variations, right? So we just write it down and to see how the computation works. So okay, so there's a setting. Yeah, so a Tori variety is Q Gorenstein. If it satisfies some cone conditions, right? There are some rays such that there's a if you given a cone, then there are a bunch of rays such that the inner product with the n tau is 1. Yeah, and for the terminal condition, we have that all the primitive vectors with inner product with n tau is bounded by 1 are only this ray we are taking from the Q Gorenstein conditions. Okay. Yeah. So in particular, we know that if your U is not a vector included in this state, the inner product will be strictly greater than 1. Okay, and And the proof is, okay, so what does minimal mean? Minimal means that in the sense of integer programming. So given two vectors in your lattice, u1 and u2, if u1 is less or equal to u2 with respect to the cone sigma, it means that the bigger one is the smaller one plus some non-zero vector u prime when u prime is in the cone. Okay, yeah, so we say that u in some subset A is called minimal. It means that it is a minimal element. It is with respect to this partial order. Okay, so okay, so the core of the core of this result is try to analyze the minimality and the inner product with respect to m tau for a given single cone tau. Yeah. So I proved that a primitive vector is middle in the interior of single cone, then the inner product is less or equal to 2. Okay, so then this is let me just so this is just the like linear algebra computations that you take inner products, then you plug it in to estimate the lower bound of such inner product. And finally we get that we get the control policy statement. If W is not minimal, then the inner product with m tau is strictly greater than 2. Okay, as long as we have this result, then the main theorem immediately follows. Yeah. So we know that actually m tau inner product with W is actually give you the log discrepancy, right? Okay, so assume assume the discrepancy is less than 1, then we can get that the inner product with respect to m tau is bounded by 2. So by the previous proposition, we know that such W is a minimal element in m tau circle intercept n. Okay, yeah. So then we apply the result from Ishii and Kola. We can say that such W will induce a Nash variation. Okay, so we have proved this result for Tori singularity, which is terminal. If the divisor E has discrepancy bounded by 1, the induced variation is Nash. Okay, so we have a statement. Discrepancy bounded by 1 imply is Nash. So maybe you will ask, how about the opposite? So for the opposite, we also have some result. We use some like integer programming theorem to show that if your variation is Nash, then the discrepancy will be bounded by 1 for Q-Gorenstein, Tori free-fall, and Gorenstein, Tori n4 for n is greater or equal to 4. Yeah. So yeah, for this result, you see that I don't add a condition of terminal. We just need that this variety to be Q-Gorenstein will be enough. Okay. Yeah, but by this result, using some integer programming result. So we still need time to check that this result is true or not. Okay, but for terminal 3-4, but yeah, for Tori terminal 3-4, there are only 2 possibilities, right? One is secret quotient, the other one is affine cone of P1 plus P1. So the next problem can be manually checked by hand. Okay, so, and furthermore, we know that for 3-dimensional secret quotient terminal singularity, it omits the so-called economic resolution, which means in this resolution, all divisors having discrepancy that bounded by 1. So this also proves that like in the first case of the Tori terminal 3-fold, we have variation is Nash, imply discrepancy is bounded by 1. Okay, and we notice, okay, so we notice that, okay, you see that discrepancy bounded by 1 is kind of like a potential criterion to see that a variation is Nash or not. Yeah, and we notice that and Kola and Johnson and by Chen Xinggu, they have some result about the Nash variations over CA type singularities or CA over R singularities. In particular, Chen Xinggu he shows that for the threefold terminal singularity of type CA over R, if the discrepancy is bounded by 1, then the corresponding variation is Nash. Okay, so we can propose two potential conjecture. The first one is, okay, discrepancy bounded by 1 imply it is Nash. The second conjecture is maybe much more weaker. If E computes the minimal log discrepancy, then the induced variation is Nash. Okay, okay, so are they true? Based on our current result, these two conjectures might not be true. Okay, so this is the last part of my research. Okay, so again, for part 2, the result is still not 100% confirmed that it's correct. Yeah, so if you found some mistakes, yeah, you can welcome to let me know. Okay, so the final case is free-fall terminal singularity with higher Gorenstein index. Okay, recall that from Mori's classification of such terminal threefolds, we have this bunch of result for classification. Yeah, if XX is a free-fall terminal singularity with higher index, then it is isomorphic to one of the following cases. Yeah. Okay, and we know that for free-fall terminal singularities, we can use the so-called weighty blow-up to study their birational geometry. We have Hayakawa, Kawamata, Kawakita, and Red, and a lot of people they have a bunch of works, and in particular by Professor Chen, he has proved that for any terminal free-fall singularity, we can use the such weighty blow-up to construct a special kind of resolution, which is called feasible resolution. Okay, so this is a theorem by Professor Chen. So given a free-fall terminal singularity, there is a sequence of probable birational morphisms such that Xn is smooth, and each step of the birational morphism, they are the so-called birational contraction to a point, which is obtained by weighty blow-up of the empty space. Okay, so it seems that this is weighty blow-up of the empty space will be a fundamental tool for studying resolutions. Okay, yeah, and okay, so essentially we use the weighty blow-up to study the resolution of free-fall terminal singularity. Okay, and other notice, we know that from Mori's classification, any free-fall terminal singularity can be embedded as a hypersurface of a cyclic quotient of C4 as its ambient space. Its ambient space is toric. We know that toric is Nash variation has been solved by Ishin and Kola. So it is natural to ask that, okay, if we have a free-fall terminal singularity, X, which is of a form of a hypersurface in C4 quotient by some vectors, is there any relationship between the Nash variation of the ambient space and the Nash variation of the inside hypersurface. Okay, so the idea is we try to use the Nash variation in the empty space to study the Nash variation of the inside hypersurface. So this is our main idea. Okay, so yeah, I have five more minutes, right? Okay, yeah. Okay, so let's consider this scenario. Okay, so by consider the by the feasible resolution with that y tilde to y to be the associated homomorphism such that induce a feasible resolution of x, and that E be an extensional divisor appearing on y tilde, and Ex to be a strict transform onto the feasible resolution. Okay, then we can. Okay, so right now we have focusing on a divisor E. Outside is called E, inside is called Ex. Okay, then we consider the set of arcs, which can be lifted in such that the arcs are based on the divisors. Yeah, it's something like we have divisors, then we consider arcs which can be lifted into these divisors. So both inside and outside. Then we consider the closure of it, which are usually called the divisorial maximal divisorial set of E. Yeah, so we can notice that if E is an essential divisor, then its N is a Nash component. So and EY, if E is essential over Y, then this is a Nash component. If Ex is essential over X, then this one is a Nash component over X. Okay, so our work is try to analyze the behavior of these two sets. Okay, so this is the main result we want to use in this scenario. So if a strict transform onto X is irreducible, my advisor and I show that the maximal divisorial set inside will be the intersection of the maximal divisorial set and the arc space of X. Okay, yeah, okay, and okay, so the proof is pretty technical. Yeah, so the proof essentially wants to show that okay, we have a left containment and a right containment. Okay, and the left containment is not hard because we know that so the point is we know that for terminal threefold, the singularities are isolated. So the smooth part of Y tilde in the set E will contain an open set of E, so including the general of E. Therefore, the closure of the circle set will be contained in the intersection. Okay, the other part is much more technical. So the other part is okay. We know that this one is contained in this one. So we can write W as a complement of this guy in this guy. Okay, this is this is kind of like a set algebra for studying arc spaces. If we can show that W is thin, then we can immediately show that by some topology we can show that okay, any X, X will be contained in the intersection. Okay, and so this containment is using that okay, outside space is toric. Therefore, the maximal divisorial set in the empty space can be written as the opposite of the toric actions and taking union. Okay, as long as we can write in this form, then by some further computations, yeah, this is this is a very long process. Then so we have a bunch of containments need to argue. But anyway, if the argument is correct, we can show that this W, which is defined to be the complement of the intersection, is a thin set. Okay, so as long as this guy is correct, then we can try to then we can try to work on this example. Okay, so this is a proposition I have done. So that X be a free four-terminal singularity of type CAX over 2. If the previous argument is correct, then it has a unique Nash variation. Okay, so the proof is kind of like, okay, we know that for the MBSX Y, it is of this form, C4 over 1/2 0 1 1 1, and this is toric, right? As a toric variety, its Nash variation is only this guy, 1/2 0 1 1 1. Okay, then we can try to consider a feasible resolution of X, and we know that because all Nash variation will coming from some weighted blow up, so the variations of X will be greater or equal to the variation induced by this vector plus 1 0 0 0, because all devices, they are inside the cone. Okay, then okay, and we know that because it is inside the cone, so the corresponding M bin variation is not Nash over Y. So therefore, the corresponding maximal divisible set is not Nash. So there must be a bigger set contain it. So we have this statement. Okay, and this is another result. This is another result by Ishii. We know that if a maximal divisible set has a contain relation, even only if we have a opposite partial order relation. Okay, and yeah, and actually this is a part I still checking that is correct or not. If I restrict this divisor onto the inside hypersurface, I do some local computation to see it is irreducible. Yeah, as long as my computation is correct, then we will have that. Okay, the maximal divisible set of E of X will be contained in the maximal divisible set induced by 1/2 0 1 1 1. Okay, so what does it mean? It means that if EX is a induced Nash variation, its maximal divisible set will be essentially of this form. So this proves that such X has only one Nash variations. Okay, and yeah, this is just the only case I have finished. I still have other kinds of cases I need to work on. Okay, and there are some references. Okay, let me stop here. Thank you.
Thank you very much. So any questions? So in your pool, you mentioned something about thin set. So what does it mean by thin set?
Yeah, thin set means that thin set means that okay, so it means that it is a set of arcs, but this arc is contained in some power closed subset in our ambient space. Right. So when we have a variety X, okay, then we consider its arc space L infinity X. and we have a W. So we say W is thin. What does it mean? It means that there is a closed subset C containing X.
You mean proper closed subset?
Yeah, proper closed subset. Yeah, proper closed subset, such that this W is contained in the arc space of C. Yeah, so it means that it is contained in a small arc space of some proper subset of X. Yeah, so, and in a point of view of multi-V integration, things that plays a role that if you plug in this set into the multi-V measure, you'll get this set is measure zero in some sense.
And any other questions?
So if you take a Nash component, so how to see that the image of a Nash component in the resolution of singularity is a divisor? So why it is a codimension one?
Oh, you mean take a
Yeah.
Nash map?
Yes.
So okay, so precisely it is not necessarily a divisor. So if your resolution has some like codimension to irreducible component, irreducible like codimensional extension set, then it might be made into that.
But you have injection from
Say the Nash, the image of Nash.
yes.
Okay. So you are asking that why does
For
it
instance,
map to,
why
does it map to the divisor?
Yeah.
Oh, okay.
Or is it easy to see or not easy?
Okay. Yes.
But on resolution, you already fixed the resolution of x tilde. So you yes.
Yeah.
And theorem said, okay, Nash components are all essential. So it will be a divisor. My question is why it needs to be
Yeah. So okay, so let me think. Codimension. Yeah. So okay. It's not hard because so the reason is because if you think about the resolution from Y to X, then it can induce a map from the arc space of Y to arc space of X,
Yes.
right?
Yes.
Okay. And furthermore, this map is a continuous bijection outside the
Exceptional
locus, right? Okay. So and here you can, and here if you consider the generating point of the Nash components, you can show that you will be lived into the generating point of the whole model, which is a codimension one. Therefore, you will be a divisor. Yeah, because you'll map to a generating point of some of the essential set of a higher model.
Okay.
That's okay. Maybe we can talk about this later.
Okay. Thank you.
Any other questions? Yeah. So in your proof, it seems that you try to compare the valuation of ambient space and also the valuation of the
inside space. Yes.
Yes. But so are you taking the restriction or what? Because in general, the valuation of the ambient space restrict to the subspace does not induce a valuation. It's just something weaker.
You mean induce semi variations?
Yes.
Oh yeah. So yeah, but in this case, it is right because I I take your feasible resolution. So, okay, so all the divisor inserting in the empty space will induce irreducible divisors in your hypersurface, which can induce a variation, a true divisorial variation, not just a semi variation. Yeah. If it is not irreducible, yeah, it might produce semi variations. Yeah.
Yes. Okay, so if there's no more question, then let's thank Lin Genghong again. Yeah, thank you very much.
Thank you.